we will continue flipping the classroom Monday. So Monday will just be a let's work some problems out together. And if you have questions from product and quotient rules from Wednesday's assignment, then I can come by your desk and help you to work those and see where your confusion was. But today, let's go on a little bit. We don't necessarily get to harder types of problems, but we get some more trig rules and we learn a little bit more about rewriting. So please write these with me and work them out with me. Example 6a. First off, what if we have something that looks like this? Well, that's a quotient. Do I necessarily need to do quotient rule with it? No, because I could realize that it's just a constant in the bottom. So it's really like a 1/6 times that x squared plus 3x. And that's a whole lot easier and faster to see it as a constant rather than to run through the quotient rule. So the derivative with the constant out front, it's just the constant times the derivative of this, which is 2x plus 3. And then you would probably put it back over 6. All right, let's do B. There's different ways that we could have left that final answer. So there were different right answers, right forms of the answer. What if you have 5x to the 4th over 8? Well, we could do quotient rule, but since 8 is just a constant and it's the only thing in the denominator, it's easier to see it as 5/8 times x to the 4th. So when we do the derivative, it's just 5/8 times that derivative. Normally we would just bring the 4 down and multiply it, which we can. I just separated it a little bit, but you definitely can just do that. So put 4 over 1. So that's 20 over 8, or reduce those by 1 and by 2. Reduce those both by 4, I mean. And you would get 5/2 x to the 3rd. So you didn't like what I just did? Then you made it a fraction, and you just got 20 over 8 x to the 3rd. And then you reduce 28ths by 4s, and you get 5/2 x to the 3rd, or 5x to the 3rd over 2. I don't technically have a preference between these two forms. I'm happy either way. C part. What if you have this crazy looking problem like -3 parenthesis 3x minus 2x squared all over 7x? Well, I'm still going to see maybe. Let me show you what I see. I see a constant, and then I see these terms, and I notice they all have x's with them. So we could reduce an x or divide an x out of everybody, which would leave -3/7 times 3 minus 2x over 1. Wow. That was a lot of rewriting, but you would probably agree rewriting is easier than taking the derivative of the quotient, maybe? So then y prime is just the constant times your derivative of this, which is 0 minus 2, just -2. Put that over 1 and multiply your fractions. Now, Monday, if you want me to go through with the quotient rule and do these, I will. D is y equals 9 over 5x squared. Do we have to do quotient rule? Since 9 is the only thing in the numerator, and it is just a constant, and since I'm able to bring that x squared up to the numerator, more so that I can rewrite it by seeing it as 9/5 x to the -2 by bringing that x up to the numerator. I'm probably not going to do quotient rule. I'm going to do it this way. So the derivative is 9/5 times negative 2x to the negative 3, right? Because we remove one, or go down one. So it's negative 18/5, which starts a fraction for me. And I'll put x to the 3 in the bottom to get rid of that negative power. So rewriting is very powerful and very handy. All right, let's get the derivatives of the other 4 trig functions. The derivative of tangent of x is secant squared x. I honestly don't know why. When we get into the spring, we can talk about how we can't do the integration, which is like the opposite of derivative, and get back. When we integrate secant squared, we get back to tangent. But I'm not exactly sure why it works that way, but that's just it, and we just memorize it. And the derivative of secant x is secant x tangent x. Secant x times tangent of x. So notice both of those are trig functions that don't start with a co. So let's put their cohorts up here. The derivative, if I could only, I forgot my with respect to x here. If I could only see your faces and see your eyes roll when I said that. Let's do the derivative of cotangent, right up beside where we did the derivative of tangent. Now, you might remember the other day I told you whenever you take the derivative of a function that starts with a co, you get a negative. And would you believe that instead of it, so the derivative of tangent is secant squared, derivative of cotangent is negative cosecant squared. Like these co's like to stick together. What about the derivative of secant x is secant x tangent x? What do you think the derivative of cosecant x is? It's the co of that. So it's a co, so it's negative. And derivative of secant is secant x times tangent. Derivative of cosecant is cosecant x, cotangent. So really kind of funny how these co's work on these two sets of derivatives. All right, so these are also on my wall by the door. Now let's do a little work with them and see how it goes. Example 8. A part. Y equals x minus tangent x. Let's do its derivative. Well, that's 2 different terms, the sum of 2 terms. We'll do the derivative of each individually. The derivative of x is 1 minus the derivative of tangent is secant squared x. And that's it. B part. What if we want to do the derivative of x secant x? This is a little different. This brings us back to what we learned on Tuesday. This is a product of 2 different things. This is my first term, my first factor. This is my second factor. So it's a product. We've got to do product rule. So when we go through and we run through the product rule, it's first times the derivative of second. We just learned the derivative of secant x is secant x tangent x, plus second, which is secant, times the derivative of the first, which is a 1. All right, and then we clean it up. We just sort of drop those parentheses. Whoops. And I don't need the times 1. That's a great answer. I love that answer. The book might get a little fancy and say, hey, let's just factor the secant x out, which would leave x tangent x in the first term and a 1 in the second term. But I'm happy either way. Those are both Lovely answers. All right, example 9. Differentiate both forms of just means take the derivative of both forms of y equals 1 minus cosine x over sine x equals cosecant x minus cotangent x. Okay. So this first form, probably going to see that as a quotient. I could get fancy with trig identities and say, I love math, and rewrite it as 1 over sine x minus cosine x over sine x. But 1 over sine x is cosecant, and cosine x over sine x is cotangent. That's why they got that other form, because they did some I love math. So we don't have to worry about simplifying it this time. We are just going to do what they said, and let's differentiate this form. So I'm going to rewrite it over here. Y is 1 minus cosine x over sine x. Well, no way around it. That's a quotient. So we're going to do quotient rule. We've got our high and our low. Well, quotient rule says low d high. Derivative of 1 is 0, and we got minus. The derivative of cosine is negative sine x. So that's low d high minus high, so write the high down. D low, the derivative of the low is cosine x, all over low squared. All right, let's just look at this first term in the numerator. A sine x times the negative of a negative sine x. So let's just make that positive. So what's sine x times sine x? Sine squared x. Minus. Want to distribute here with the cosine? Minus cosine x minus cosine squared x all over. Since everybody else is getting written this way, why don't we rewrite this way as sine squared x? Okay, let's distribute the negative 1 here now. All over sine squared x. Oh my gosh, I'm having flashbacks to pre-calculus, where our favorite Pythagorean identities kept popping up over those first a couple of days. And I was like, if I had $1 for every time we saw this, what is sine squared x plus cosine squared x? It's 1. So we get 1 minus cosine x over sine squared x. And they're letting us leave it there. I thought they were going to make us do a trig identity and reduce that. They're letting us leave it there. So that's what this one equals. The second form was y equals cosecant x minus cotangent x. Well, I love this form so much better because it's just two things that I can just take derivatives of. Derivative of cosecant x is negative cosecant x cotangent x. We just learned that. Minus. See how I immediately prompt a parenthesis? So I did a minus and I started a parenthesis. That is just such a good idea because you never know when you might need to distribute a negative. So minus the derivative of cotangent x is negative cosecant squared x. Then if we clean that up a little bit, a negative times that negative gives me positive. Negative 1 times it, I guess. Okay. So that way I got that answer. That way we got this answer. Both of these answers are great. but they don't seem to match right now. But I guess we could factor out cosecant from both of these terms. I don't know if that helped us much. Cosecant's the same thing as 1 over sine. So let's put that over sine. Does that help us much? Not a lot. Not a lot. Cotangent is cosine x over sine x. Cosecant is 1 over sine x all over negative sine x. So these two things here have a common denominator. So I'm going to write that as cosine x minus 1 over sine x all over negative sine x. Let's make that bottom a fraction and flip it up here and multiply by its reciprocal. So we're not going to divide by it anymore. We'll multiply by its reciprocal. And you get cosine x minus 1 all over negative sine squared x. So it's very similar to that. My signs are just wrong. My SIG and S's are just wrong. Cosine's positive, 1's negative, and it's the opposite. And sine squared's positive here, and it was negative. So we could just run through and multiply everything by a negative 1 on the top and the bottom. And now they match exactly. They match exactly. Alrighty. What else do I need to tell ya? Let me see here, my friends. Alright, last thing, almost done. Just as we know that we can get from the position function, hopefully you've got that video watched yesterday. If not, go to Google Classroom for Wednesday and watch your video about physics. The position function is s of t. We learned that the velocity function, which is v of t, was actually equal to the derivative of position. Well, it turns out that acceleration, how do I spell acceleration? 1L, which is a of t, is the first derivative of velocity, and it is the second derivative of position. Wish I could whistle. The second derivative. One way to talk about a second derivative is to do a double prime mark like that. If you think about what the topic title was, it was product and quotient rules and higher order derivatives. So we aren't just going to do a derivative, which is also called a first derivative. We're going to learn how to take second and third derivatives. So it's super nice. If you have f of x equals 5x to the fourth plus 3x squared plus 19x, we can jump in and do a first derivative, just using our rules. 20x to the third plus 6x plus 19. Well, that was fun. Let's do it again. And we'll call it the second derivative. That would then be 60x squared plus 6. So it got smaller. Now we only have two terms. That's okay. Let's jump in and do a third derivative. That's 120x, and the 6 drops off. They do not do 4 prime marks like that. They would say the fourth derivative like that. And so that would just be 120. And if we did the fifth derivative, it's 0. And every derivative after that for 0, the sixth derivative of 0, 0 is constant, derivative of constant is 0. Every derivative after that is 0. So, pretty cool that we can do that. We will do this example 10 and the example 10 from 2.1 when we're together Monday. Have a great weekend. hopefully these examples that I did for you will help you to tackle the homework questions that I posted for you. All right, and we will just work together Monday. We'll just put our chairs together and just work hard on problems.